making molecules mass to mass conversions. So the chemical equation, like we were just talking about, gives us conversion factors between moles of reactants and moles of products. But we're interested in relationships between masses because we have balances. We can weigh the products, we can weigh the reactants, and so that's a much more practical thing. So what we do is we do this. And this is kind of the big idea of stoichiometry, that big new word we learned here. Didn't mean to do that. So grams to moles to moles to grams. So remember I said that making these paths was a little bit like Dora asking the map which way to go, right? So this path is going to be a very, very common path. We should almost like have it paved because we're just going to go down this one particular path so many times. And so grams to moles to moles to grams. And that's something that you should just kind of chant to yourself. If you wake up in the middle of the night thinking grams to moles to moles to grams, then you're studying enough, right? Grams to moles to moles to grams. That is stoichiometry in a nutshell right there. So what this is, we just learned how to do this piece in the middle, taking moles of one thing and figuring out moles of another thing. We got that ratio from the balanced chemical equation, the mole ratio. We have actually already learned how to do the first step and the last step. This is going to use the molar mass of this compound. We're going to take a mass in grams and we're going to convert to moles using the molar mass. Remember, the molar mass is where we looked at the periodic table, and if we had 1 carbon and 2 oxygens, we found the mass of each of them and we added them up, and that was the molar mass. So we convert from mass of compound A to the number of moles, and then to the moles of the other compound, the one that we're trying to find out about. And then we use the molar mass of that second compound to find the mass of the second compound. This is the big idea, the big picture. If you can keep the big picture in mind, you're much less likely to get lost when you're on the journey. So here's an example. Here we have a balanced chemical equation. This is for the combustion of octane, C8H18, reacting with oxygen, forming CO2 and water. And the question is asking us, what mass of carbon dioxide is emitted by an automobile for every 5.0 times 10 to the 2 grams of pure octane that's used? Well, the balanced chemical equation can help you to organize the information from the problem. So we can use this balanced chemical equation to organize this information. So reading the question again, what mass of carbon dioxide? Okay, we have learned stoichiometry, and even if you were kind of shaky on it, hopefully you're going to do well enough that you can pick out which of these is going to be carbon dioxide, right? You've got 4 choices. We know that this is oxygen, and this is water, and so this one has oxygen in it and carbon, so this must be the carbon dioxide. The question is what mass? The mass unit that we use in chemistry is grams, and so I have to start writing first. Question mark, grams. How many grams of that? That's what we're trying to figure out. And then they're giving us this number, grams of pure octane. That's this guy. That's the only one that we don't have a clue about the name. So this must be the octane. So I'm going to write 5.0 times 10 to the 2 grams. So now we have our starting point and our ending point. They're both in grams. We have to go to moles in the middle. Grams to moles to moles to grams. So we're going to write out our path. We're going to start with 5.0 times 10 to the 2 grams of what? Of C8H18. And we're going to convert that to moles of C8H18. And then we're going to go to moles of the other thing, moles of CO2. and then to grams of CO2. So this is our starting compound. This is our ending compound. The first two are the starting one, C8H18, C8H18. The second two are the second one, CO2. And then it's grams to moles to moles to grams. What's happening is we're converting here from grams of one thing to moles of the same thing. We can only change one thing at a time. At the end, we're going from moles to grams of the same thing. This piece in the middle that we just learned how to do, the unit is the same, the substance is different. So we're not changing the unit, we're just changing which compound it is. So we're always changing one thing at a time. So getting this path written out, that is the key step in doing stoichiometry problems. After that, it's following the pattern of dimensional analysis. So I'm going to have 3 steps, 3 fractions, because I have 3 arrows. So I'm going to put all my units in first, and then I'm going to mess around getting the numbers. So grams of C8H18 times and a line, times and a line, times and a line. Grams to moles to moles to grams. These units you just copy down in the numerator. So grams of that to moles. And yes, it's tedious at times writing all those silly formulas. Just do it anyway. So I have the numerator from my path. I'm just copying it. The numbers in the denominator are just the previous unit because I want those units to cancel out. So I'm going to have grams of C8H18 down here because those are going to cancel. And then I'm going to have moles down here. And then over here, I'm going to have moles of the other thing. Make sure that your units actually cancel out. Because moles of CO2 do not cancel moles of C8H18. It needs to be the same thing. Any questions about how I got the units in there? If you didn't get dimensional analysis figured out in your head at the beginning of the semester, now is the time to get it straightened out, okay? And if you have questions, please ask me. So now we need numbers. The middle number is the easy one, this middle term. We just go look at the equation. In front of C8H18 is the number 2. So we put number 2 in front of moles of C8H18. What number should I put for the moles of CO2? 16. Because up here, there's a 16 in front of CO2. So I'm going to put 16 moles of CO2 here. For every 2 moles of C8H18 that get burned, I produce 16 moles of CO2. That's what the chemical equation is telling me. Now, this first term and the last term are molar masses. Okay, so we're going to use the periodic table, and we're going to use the formula that was provided here, and we're going to calculate that. And I would encourage you to actually write this out just off on the side somewhere. So C8 means 8 times the mass of carbon, and 18 times the mass of oxygen. .224. And as usual, I didn't leave enough room in there. 114.224. That number is always with the grams. A molar mass is the mass of a mole, 1 mole. And then we've got CO2, so that's 1 carbon and 2 oxygens, which is 44.01. So then over here, that number goes with the grams. and for 1 mole. Now you go left to right, top to bottom. So I've got 5.0 EE2, multiply by 1 if you like, divide by 114.224, times 16, divided by 2, times 44.01, divide by 1 if it makes you feel better, equals, it's not going to fit up there, so I'm going to write it down here. This is what my calculator says. And that will be grams of CO2. How many significant figures should that have? It should have 2. The mass that we started with has 2 significant figures. In most of these problems, it's going to be the mass that you're given that limits the number of significant figures. So if significant figures was not your favorite thing, you'll do pretty well if you just look at, well, how many sig figs in this number? There's 2, so then I'll do 2 in my answer. These numbers, this one had technically 4, and this has 4, and these are exact. So this is the smallest guy. We just need to be real careful when we round this off because we don't want to call this 15. It's 1,500 grams. It's a lot more than 15. So if we're rounding to this place, that's the hundreds place. Question?
What's the number on the very, where it equals 44.01?
Grams of CO2. This part right here?
No, you're
This one?
down. Last one.
This one?
Yeah, what's the number in front of it?
1.
Just 1?
Yeah. Stupid screen. Actually, it's the projector. So if we're rounding here, we're rounding to the nearest hundreds place. Okay? And my 3rd grader was doing this, so I know that they taught you this in school. You've just repressed it or something. So rounding to the nearest 100, this would be 1,500, right? Grams of CO2. A better way is to put it in scientific notation first and then round it off, and then you won't have troubles with the rounding to crazy numbers. So that would be 1.5 times 10 to the 3rd grams of CO2. That's the best answer. You had a question?
Can you remind me how you put the 500 times 10 squared
into the calculator? Yes. So here we have scientific notation, and we haven't used that for a little bit. So let's see. So that would be 5.0, and then you're going to use the EE button or the EXP button, whichever one your calculator has, and then just the exponent. Because that EE button does times 10 to the for you. It's a shortcut. So don't go throwing in an extra times 10. Any other questions? Can you get your calculator to give you this answer? That's important. Because getting this all written out, I mean, that's really the hard part. And then if you're making a little tiny mistake on your calculator every time and getting the wrong answer, that's just like a huge bummer because you understand the chemistry, but you're coming up with the wrong answers and then you're not going to do well on an exam, right? Yes?
Sorry, last question. Which way would you accept it? Like, out of the 3 answers you gave, which one do you want?
This is the best answer, the one at the bottom. Which answers are accepted kind of depends on the question. This question did not state that it wanted the answer in scientific notation. If the question says express your answer in scientific notation with the correct number of significant figures, then it has to be this one at the bottom. If it doesn't say, like on a lab, if you gave me all these digits, I'd probably just make a little note there that you've got way too many sig figs, but I wouldn't count it wrong. Mastering chemistry, can be pretty particular about things like that. And so you have to figure out what the person who's asking or the thing asking the question wants and give them what they want. And then everybody's happier. Any other questions? We're going to do some more examples. Here's another one. Milk of magnesia. I started reading the second line. Magnesium hydroxide, which is the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to this reaction. So here's magnesium hydroxide reacting with HCl to form water and magnesium chloride. What kind of a reaction is that? Is that a precipitation reaction? No. It doesn't form a solid. It's an acid-base reaction. This is a base because it's got OH. This is an acid because it starts with H. Acid-base neutralization reactions form water and an ionic compound. Okay, so that was just a little review. Here's the actual question. How much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? So I made some space here on the slide so that we can write these numbers in. So 5.50 is the mass of that compound. So I'm going to write its mass right under the compound. And the question is, how much HCl in grams? So HCl, that's this guy, question mark, grams. Okay, this tells us what we're starting with and what we're trying to find out. So then we need a path. We're going to have 5.50 grams of magnesium hydroxide. And way at the other end, we're going to have grams of HCl. And what do we chant? Grams to moles to moles to grams. So we're going to take grams of magnesium hydroxide and convert to moles of magnesium hydroxide. And then we're going to convert that to moles of HCl and then to grams of HCl. Grams to moles to moles to grams. So I'm running out of room down there, so I'm going to make some room up at the top by getting rid of this stuff. It's like a black cloud. There. So I can't see the edge of the screen. Oh gosh, I can't see the edge of where I'm going. I don't want to write. So we're going to have an equation here with three fractions, three conversion factors. So 5.50 grams of magnesium hydroxide times in a line, times in a line, times in a line. And that's going to equal something. So we just copy everything down. Grams of magnesium hydroxide to moles of magnesium hydroxide. To moles of HCl to grams of HCl. And then we're going to take the previous term and bring it down into the denominator. So I'm going to have grams of magnesium hydroxide here. And moles down here. And moles of HCl down there. So these units cancel out. They're same on top and the bottom. Any questions? All the units in first, then the numbers. The middle term is the easy one because the numbers come from the balanced chemical equation. There's a 1 in front of magnesium hydroxide, so I'm going to put a 1 in front of magnesium hydroxide. There's a 2 in front of the HCl, so I'm going to put a 2 in front of the HCl. And then I need to calculate molar masses. So magnesium hydroxide. How many magnesium atoms are in one of those units? Just 1, right? So 1 at magnesium is 24.31. How many oxygens? 2. OH is a group, and there's 2 of them. That means there's 2 O's and 2 H's. So 2 times 16 and 2 times 1.008 for hydrogen. I'm getting 58.326, but I feel like I may have pushed a button wrong. Anybody else get that? Okay. So that's the molar mass of magnesium hydroxide. That means that 1 mole of magnesium weighs that amount in grams, 58.326 grams. And then I need the molar mass of HCl, which is 1 hydrogen and 1 chlorine. So 1.008 plus 35.45. 36.458. That's not a 5. See, I'm so brilliant today. 36.458. Got all my numbers in, my units all cancel out. Now I just do the math. 5.5 times 1 divided by 58.326 times 2 divided by 1 times 36.458 equals, how many significant figures should my answer have? 3. I started with 3. So 6.88 grams of HCl. Any questions? Here's another example. One component of acid rain is sulfuric acid, which forms SO2, a pollutant. Forms when SO2, a pollutant, reacts with oxygen and rainwater according to the following reaction. Okay, that's really interesting and all, but we don't actually need to know that to do this problem. Here's our balanced chemical equation. Assuming that there's more than enough oxygen and water, how much H2SO4 in kilograms forms from 2.6 times 10 to the third kilograms of SO2? They gave us kilograms. That wasn't very nice of them, was it? Well, let's take this information and write it under the balanced chemical equation. So I've got a number here. It's 2.6 times 10 to the third kilograms. And then they're asking me to find the amount of H2SO4 in kilograms. So what was our chant? Grams to moles to moles to grams. But they gave us kilograms, and they're asking for kilograms.
So 2 extra steps, or can you just...
We can, there's different ways to approach this. We can do 2 extra steps. So we can go grams to moles to grams. That's what we normally do. and then we could convert to kilograms at the end, and at the beginning we could go from kilograms to grams, so we could do that, right? What we'll see, we're going to do that because this is the most straightforward way, and I want to be as straightforward as possible. What we'll see is that the conversion for kilograms to grams and the conversion for grams to kilograms are going to cancel each other out. But we'll go ahead and do them anyway. So again, I'm going to make some space up here on the top. I'm not going to use the black this time because that didn't work out very well last time. Okay, so we're starting with kilograms this time. We've got 2 extra steps. Let's see if I can squeeze it all in. 2.6 times 10 to the third kilograms of SO2. And then I'm going to convert to grams of SO2. And then I'm going to convert to moles of SO2. And then to moles of the other thing, moles of H2SO4. And then to grams of H2SO4. And this is where I ask myself, why do I do this to myself? And then it's going to be creative, to kilograms of H2SO4. So I'm going around the edge there, which is really not working for you guys because it goes off the screen. Okay, so I rewrote it so that we can get it all on the screen. So that's the units from the path, kilograms to grams to moles to moles to grams to kilograms. And now we put the previous unit in the denominator. So I'm going to put kilograms down here, SO2, and grams SO2 down here, and moles SO2 down there, and moles H2SO4 down there, and grams H2SO4. All things we've done before, it's just we're stringing them together in this one long thing. But we have a map, and so even though this is a journey of many twists and turns, we just follow the directions and we'll get where we want to go. Now we need numbers. The one in the middle is the easy one. Why not start with the easy thing, right? What do I put in front of H2SO4? A 2. And what do I put in front of SO2? A 2. Now, if you want to cancel those out, you may, but I'm just going to put them in my calculator. Our first term here, kilograms to grams. What does kilo mean? It means 10 to the third. So I have kilo on the bottom. I'm going to put what it means on top because I'm not going to put them together. So I'm going to have 10 to the third on the top. And then to help me remember how to put that into my calculator, that's 1 times 10 to the third. And then as long as we're talking about kilograms, we might as well take care of this guy at the end. Here at the end, kilo is on the top, and so we need the 10 to the third on the bottom. 10 to the third. Do you see how those guys cancel each other out? 10 to the third grams, 10 to the third grams. How about we just cross those off right now? You guys okay with that? Or would you rather not? Somebody made a face. We won't. It's okay. So we got those guys. Now we need grams to moles. We've got the formula right there, SO2. All we need is the periodic table and the calculator. But let's write it out so we don't go astray. We've got 1 sulfur, and 2 oxygens. So that's 34.07. No, it isn't. It's, yeah. See, this is what happens when I try to do things in my head. It's 64.07. The calculator in my head is broken today. Maybe it's a solar calculator, and that's 64.07. It doesn't have to be pretty. H2SO4. There we've got 2 hydrogens, 1.008, and sulfur, and 4 oxygens, 1.008 times 2 plus 32.07 plus 4 times 16 equals 98.086. And so we're going to squeeze that in here, 98.086. It's all messy and cramped, I'm sorry. Let's double check that our units cancel out. Kilograms of SO2, grams of SO2, moles of SO2, moles of H2SO4, grams of H2SO4. We're left with kilograms of H2SO4, which is what we want. 2.6 EE3 times 1 EE3 divided by 64.07 times 2 divided by 2 times 98.086 divided by 1 EE3 equals, and the number I'm getting is 3980.390198, and this should have 2 significant figures. Let's put it in scientific notation first. Okay, and hopefully at this point we recognize, oh, wait a minute, that's plenty. I'm going to stop here. Where did I move the decimal point? I moved it 1, 2, 3 places, times 10 to the third, and I'm stopping right there. So that's going to be what? 4.0. The 8 causes the 9 to round up to a 10, which then bumps the 3 up to a 4. But that doesn't reduce us to 1 sig fig. We need to put the 0 in there because there's 2 significant figures. And so our final answer is 4.0 times 10 to the third kilograms of sulfuric acid. And messy problems like that really need a box around the final answer. Any questions? Yes?
Did you cancel the 1 times 10 to the third because it's the same as the?
You can cancel it because it's the same. If you have something in the numerator like this that is exactly the same in the denominator over here, you can cancel them out. I did actually do it on the calculator.
But if that wasn't there, we would have to like add that in. You know?
Well, actually, when I included it when I did the calculator, I did this times this, and I did it, and they did cancel out. If you're more of a math person and you see, oh, well, those cancel out, then you don't necessarily have to type them into your calculator. Any other questions? What's next? Oh, good.